Hello, hello, everyone. Welcome to another Sunday tutoring session with me, Melissa Maribel. So happy you can join us today and just be a part of this chemistry learning community. I also wanted to go over really pretty much just what you guys are on right now. I keep asking you every single time because it keeps changing, and I know that everyone is just on different topics and different subjects, and I'm really trying to just get these Sunday sessions to help you guys as much as possible, so covering everything that you guys are on right now. So at any point, go ahead and leave in the chat, leave a comment below, let me know what you're on, what you need help with, what you want me to cover next Sunday, or maybe in another video, or so on. And you also might already know that I'm doing something very cool, that if I reach 10,000 subscribers with your guys' help, I will do an 8-hour long live tutoring session. Yes, you heard that correctly, 8 hours. So please share my videos, tell people in your class or your friends or your teachers, anyone who you think will benefit from these videos. Please spread the word and help us get to 10,000 subscribers. And I'm pretty much just going to be doing this for your guys' finals so you can succeed on your finals, because I know the chaos of finals week. Trust me, I've been there a lot of times. So why don't we go ahead and get started as more people trickle in. So today we're focusing on periodic trends and all the different types that we see in that, like electronegativity or electron affinity and so on. Then after that, we're going to move on to redox reactions. So that's oxidation and reduction. So if you're looking for that specific topic, hang on, that's going to be towards the end. And we're going to focus on a lot of redox reactions, because I know that gets confusing, as well as oxidation numbers. So let's dive right in. All right, the first topic that we're going to be talking about is electronegativity. Now, with electronegativity, I just want to go over like the concept as a whole. We use this a lot, and I don't know if you saw my last live tutoring session where I talked about polarity. Electronegativity is basically the concept that some sort of atoms are more attractive, per se, than other atoms. So what that's really saying is that they will attract more electrons. So if that atom attracts more electrons, it is more electronegative. Does that make sense? So that's the concept overall. Now we'll see here the different types of trends, or the different like increasing or decreasing portions of this. So electronegativity, as you see on the screen, it increases as you move left to right from the periodic table. And then as you go down to then up your column for your periodic table. So something to note is fluorine will be right here. Fluorine is a type of halogen, and that is actually the most electronegative atom. So what I like to think of is, if you're looking for whatever, is the most electronegative atom, what you're focusing on is what is closest to fluorine. So in case you forget this, what is it increasing? Where is it decreasing? Just think for electronegativity, the ones that will be the most electronegative are the ones that are closest to fluorine. Now, with the exception, of course, exceptions, right? Chemistry, with the exception of your noble gases, which are right here typically. And I'll show another periodic table in a second. So your noble gases are completely stable, and they don't want to give up or lose any of their electrons. They're happy. So that's why they're not going to add any electronegativity or not be electronegative whatsoever. It's your halogens that typically are very electronegative. So I'll show you another table that tells you, kind of shows you all of the different types of like actual electronegativity values. So you'll see here, it actually tells you those are not your masses overall. That's actually going to be how electronegative those atoms are. So if we'll look at fluorine, we'll see that it has 4.0. That's the electronegativity value. And if you compare it to everything else on your periodic table, that's why it's the most electronegative atom, because it's the highest. So, and then we'll also see that your noble gases, which are all right here, they don't even have anything for electronegativity. So they're an exception to that rule. So we know that noble gases are not electronegative whatsoever. It's only going to be everything in this column, which are your halogens. Okay, so remember that this column overall over here, those are your halogens. Those will be very, very electronegative. That being said, there's another little thing that I want to mention. A lot of times professors or teachers might tell you, what if you were comparing the electronegativity of oxygen or chlorine? They're both pretty close, right? If you didn't know the actual electronegativity value, then you might even say, well, it's a tie. It's not. So anything that is typically closest to fluorine, as we said, is the most electronegative. Now, chlorine is a little bit below fluorine, and then oxygen is a little bit above, and then just right next to it. So it's kind of a rule of thumb to know that oxygen would be more electronegative just because it's higher up on the periodic table. So that kind of takes preference whenever you're kind of looking at that trend, whatever is higher up. So if we're having like oxygen and chlorine, that's why oxygen wins, because of that idea of that trend, that it's higher up and it's really, really close to fluorine. So be aware of that. So if you were to been asked a question, is oxygen or chlorine most electronegative? It would have been oxygen. And we also see that with the value of 3.5 versus chlorine's 3.0. Let's try it. So that being said, now that we know that our electronegativity increases as we move left to right and from down to up, let's arrange these in increasing electronegativity. All right. So I'm just going to highlight and circle all the ones that we have here. So the first one we have is bromine. So Br is right there. Calcium, Ca is right there. Mg is right there. Magnesium, and then iodine is there. And lastly, nitrogen. So arranging this in increasing order is actually going to mean that we're going from smallest to largest. So our smallest is going to be anything on the opposite side or furthest away from fluorine. Because remember, your trend is that it increases going up and going from left to right. So anything closest to fluorine will be the highest. So then your smallest is going to be anything further down and further away from fluorine. So in our case, it would be calcium. So calcium would be the smallest. The next one up would then be magnesium. And then next we'll go into our halogens and see, okay, which one is possibly going to be better? Well, I know that iodine is lower, so that's not going to be good. So that would be lower in electronegativity. And then I'm going to compare nitrogen and bromine. And they're both pretty close to fluorine. But what if I were to go back to that concept of, okay, well, anything that's a little bit higher up is then going to be better, right? So if we were to look at nitrogen and bromine, well, bromine is barely 2.8 and nitrogen is 3.0. So nitrogen wins because it's a little bit further up, even though they both have like one space or one atom. They're both one atom away from fluorine. Because nitrogen is higher up, then that one is more electronegative. So that'll tell us that, all right, bromine is next and nitrogen is the most electronegative atom in this case. All right, let's continue on. If at any point you guys have any questions, feel free to leave a message or, a chat, a comment, anything. Let me know if you guys have questions so I can answer those right away. Let's move on to the next trend. It's called ionization energy. Ionization energy is the energy required to remove an electron. All right, so it's all about just removing electrons overall. And we're going to see which ones are higher up in ionization energy. There's also a concept that there are more than one ionization energies dependent on whatever atom you're looking at. So I'll make more sense of that in a second. But I just want us to see that the same trend applies as electronegativity for ionization energy. So once again, we're going to be increasing as we move from left to right. And as we move from down to then up the periodic table, we'll see that it would be increasing for your ionization energy. Continuing with that concept, what I meant by there are multiple or there's more than one ionization energy depending on that element, or in our case, a metal. It's always dependent on metals, by the way. So for ionization energies, you really look at it as, since we're trying to remove an electron, right? So magnesium has a charge of 2+. So we want to remove 2 electrons. Because we want to remove 2 electrons, then it has 2 ionization energies. So it has, like, it's really dependent on the charge of that metal or that atom as a whole. So like, let's say if you were to have some sort of atom that has 3 electrons or a 3 plus charge. Then we want to remove 3 electrons, thus it then has 3 ionization energies. So, and so on, that's really the concept between this. And what I'm showing here with magnesium, it starts off neutral. That's where this comes in. It's neutral, it's in its gas state. And then next, for the first ionization energy, we're showing that we're really removing an electron. That's why it's on the product side. And because it starts neutral in the reactants, and then we're removing an electron, and then now we have one in the product side. And that just shows the removal of 1 electron. Next, I'm going to keep going with that concept, now going to the second ionization energy. So that's why I take this Mg plus, because now it's a +1 charge. And then my second ionization energy is then going to be removing, again, the second electron. So you could only remove an electron one at a time. You can't do that just right off the bat. And then lastly, that's where we get our actual typical charge of magnesium 2+. That concept making some sense? So it's really just dependent on your charge of your atom. That tells you how many ionization energies you will have. And let's get back to trying some of these. So this states which element has the larger ionization energy. So we're going to be comparing these two different atoms to each other and just seeing the trend as to which one would have the highest ionization energy. Remember, our trend is that it increases going in this direction. It's also going to increase going up. So let's look at aluminum and sulfur and compare which one will have the larger ionization energy. So aluminum, which is right here, and sulfur, which is right here. So though they're on the same row, we still can figure out what our ionization energy would be. So since it's higher, as once again, we're getting closer to the halogens or fluorine in general, then we'll see that sulfur would be larger in ionization energy. So sulfur wins in that case. And then I'm going to look at arsenic. So arsenic is right here. And here's SB. And then looking at those two, they're in the same column. So then now we have to look at the increasing ionization energy as we move down and then up the periodic table. So in our case, since arsenic is higher up, then that's going to be larger in ionization energy. See how we're doing this. And then next, I'm going to look at nitrogen and silicon. And we see that nitrogen is once again higher up, and it's also closest to fluorine, or it's more to the right. So then in that case, nitrogen wins, and that has the larger ionization energy. It's really all what we're looking at. It's just knowing, just remembering all of those different trends, as well as knowing the concept and the definition. So I have seen a lot of multiple choice questions, by the way, that teachers do ask you, explain what ionization energy is, explain what electronegativity is. So definitely know those concepts, understand the definitions of them and what they are, besides just knowing the actual trends. And let's move on to a different type of trend. So you can kind of think of this as the opposite now, or really the opposite of ionization energy. Electron affinity is the energy required to add an electron. So ionization energy was the energy required to remove an electron. Electron affinity is the energy required to add an electron. And we'll see the same trend again. It just keeps going. We're going to see from going from left to right, that's going to be increasing. And from down to up, that's also increasing. Pretty easy so far, right? If all of these trends are the same, so far, so good. This is really just seeing that I just have to know it's going from left to right, that's increasing, and down and up, and that's increasing again. So knowing that, let's understand the concept a little bit further. So since we're adding electrons in this case, we're going to be looking at our halogens right now. So chlorine is a type of halogen, meaning it's in this column. And chlorine, if it's in its typical gas state, meaning it's going to be completely neutral. If we were to add an electron, we're going to add that to the reactant side. And then what's going to be produced on your product side, or the right-hand side of the arrow, then we see that that would have been our minus charge. So that's electron affinity, and that's kind of why it's really just reversed, right? So we saw with ionization energy, we're actually removing an electron, and then that electron would then be added to the product side. And then rather for electron affinity, we're adding electrons to the reactant side because we're actually adding electrons, right? So that's the overall process of this. That's the overall concept. Typically, you don't see anything with more electron affinities. That's really just ionization energy where you're going to have multiple of them. However, electron affinity, you really don't see that. So let's try a problem with arranging increasing order, once again, of electron affinity. Going back to our trend and just remembering that we're still increasing the same exact way as we move along left to right and as we move up. So let me fix this arrow real quick. So as we move right along, let's just see which one would be the smallest, because whenever it's saying we're increasing and we're going in increasing order, it's actually smallest to largest. So let's just start kind of like putting where everything is and see what we have here. So we have lithium, we have fluorine, chlorine, arsenic, and we have potassium. All right. So let's just look at the ones that are going to be furthest away from this corner up here. So meaning anything closest to fluorine once again. So anything closest to fluorine will be higher in electron affinity. Rather, anything further away will be lower in electron affinity. So in our case, the one that's the furthest away would then be potassium. It's okay. So because this is further down, right? That's why it's decreasing. So then now the next one that's really, really far away from fluorine would then be lithium. And then we're going to keep increasing now, and we'll see that the next one that is a little bit further away from fluorine is arsenic. Keep going. Now, lastly, we said that the most electronegative, the highest in ionization energies and electron affinity is fluorine. So anything closest to fluorine is a great thing to just see. Okay, that's going to be higher in electron affinity. However, we have fluorine in this case. So then fluorine would be the largest and chlorine would be next. So this is increasing order. So potassium is the furthest away and fluorine is the closest to that trend and the most electronegative, or actually, sorry, electron affinity in this case. And it is the most electronegative. So let's keep going with all the different trends. So finally, we are changing our trend. I wish it could all be the same. It'd be easier to memorize. But this is the concept of atomic radii. And atomic radii is really just looking at, you might have seen a drawing or a figure, something like this, where they put some sort of atom next to another atom. So next to another atom, and then we're just looking at really the radius of these two atoms. So there's another little concept here that it's really just talking about atomic radii is the distance from the nucleus of an atom to the outermost electron. I'm going to say that again. So if your nucleus is right here, okay, let's just say that's our nucleus. And then we're then going to the outermost electron, then this is pretty much the radius that we're looking at right here. And that's typically what they look at. Atomic radii is really kind of saying, I wouldn't say it's talking about how big the atom is per se, even though it is easier to think about that. It's more specific, of course, it's chemistry. It really talks about the distance of your nucleus to the outermost electron. All right, so continuing with that concept, now our trend is going to be the opposite. So now it's going to be larger in this corner, okay? So in this case, and by the way, that little corner is cesium. So if anything is closer to cesium for atomic radii, then that is going to be the largest. Anything that's further away, so now anything that is by fluorine is then going to be lower in atomic radii. All right. So now, as I mentioned, now going from right to then left, then we'll see that it's actually increasing for atomic radii. As we move from top to then bottom of our periodic table, that's also increasing in atomic radii. Here's a better representation of this. And here you can really just see the overall size of these atoms as a whole. And then even just looking at this concept, it really shows you the trend here. As we start to get larger than in atomic radii, this then starts to increase as we move down. As we move down our periodic table. And then also as we move more to the left, that also shows that it's increasing as well. So this is just a really good diagram telling you, okay, really cesium is going to be a lot larger in atomic radii, and that just helps us identify, where do I look? How do I remember this concept? So kind of going back to, real quick, just going back to the concept here, that ionization energy, electronegativity, and electron affinity, all of those are going to be highest when they're closest to fluorine. So any atom closest to fluorine would be higher in electronegativity, in ionization energy, and electron affinity. And then now the opposite now, for atomic radii, anything closest to cesium would be larger. All right, so just knowing those, that actually is really helpful to be able to figure out, what's higher in whatever you're looking for. So let's try one. And actually, let's continue another concept, because this also kind of goes hand in hand with atomic radii, because it's still talking radii. So it's called ionic radius. And essentially what we're looking at is ions. So remember, ions are it's an element that has a charge. So we have two different types of ions. We have cations and we have anions. Cations are positively charged and anions are negatively charged. So now we're comparing, really, are cations or anions larger whenever we have that sort of atom? So I know there's so much more that we were comparing in this sense, but let's make it a lot simpler. And really what we're just looking at is, the larger the cation, or the larger the positive charge, that means we're actually going to have something that's smaller. Right? So that's what this is essentially saying. So if we have something that's very, very large in charge, like let's say if we were to have, I'm going to say iron, and that has a 3+ charge or something like that, then that's actually going to mean that it is a smaller atom or a smaller cation, as a sense. It actually makes the original atom smaller. That's what I want you to think of. And then now if we have a larger negative charge, like let's say if we had, goodness, we can do anything. I'm just going to do oxygen's typical one. So if we had oxygen and it had a larger negative charge, then that has a larger anion. So cations typically tend to be smaller and anions are typically larger. All right. So that's kind of the concept with this overall. And then we're going to put this into practice, just understanding that again. So I'm going to say that one more time. So the larger the positive charge, that means the smaller the cation. The larger the negative charge, that means the larger the anion. All right. So if we were to, let's say, arrange this in order, for this first one, note that every single cation or every single ion is the exact same, right? So since they're exactly the same, then we're just going to kind of look at the overall trend. And your trend is going to be the same exact thing as your atomic radii. So note that it's going to increase as we move along, as we go closer to cesium and so on. So in our case, let's just figure out where in the world are these elements. And looking at this, we'll see they're all right here, right? So they're all going to be in the same exact column, or in the same exact group. So in our case, we're going to look at which ones are then going to be increasing due to that trend. So due to that trend, as we move further down the column or down our periodic table, then it starts to increase. So which one's further down, that will tell us, okay, HF. So that one is larger. And then next, this one's next, and Ti is last. So it's really just kind of going off of, first, let's look at our charges. So it's a little bit different in this case, but we look at our charges first. Since they're all the same charge, then that tells you, okay, well, they're probably in the same group. And then in that case, we're just going to look at our overall atomic radii trend, where we know that it starts to increase as we move down. So that's why this is our proper order. This is going to be your largest, and this would be your smallest. Moving on. So now let's pay attention to all of our different charges in this case. So sodium, Na+, that is a positive charge, meaning it's a cation. So we know that that's probably going to be a little bit smaller. right? And then same thing goes with magnesium. Since that's a 2+ charge, then we know that, okay, anything that has a larger cation, that means it's going to be smaller. Anything that has a larger anion or a negative charge, that will be larger. So in our case, the only negative charge that we have is fluorine, and we'll see that in a second. Which one, here, let me go back to this. Which one would actually win? So we would align this according to, and this, by the way that this was showing, this was our largest and this was our smallest. It was in increasing order. So now looking at this next type, it's called isoelectronic. I want to explain what that means. So isoelectronic is essentially just saying they all have the same electron count. Okay, so isoelectronic just means they have the same amount of electrons. So looking at that, we arrange this according to the anion or the cation. So essentially, the cation that has the largest positive charge is then magnesium. That's why it would then be the smallest. The next cation that we have is sodium. That would then be the second smallest because it's a cation and we know they're small. And which one would then be larger or the largest? That then it would be our anion, which is fluorine. So that's why this is the largest, because it's our only anion. Now, I also want to mention just how I even knew any of this. So another concept or another way to go about this is really just looking at your different types of electron counts. And let's just see if they really all would give us the same exact electrons. So let's say magnesium. Magnesium typically has how many electrons? So we have 12 electrons overall. So 12 electrons. And by the way, what I'm looking at the atomic number. Remember, the atomic number is equal to the same amount of electrons if it's a neutral atom. Now that we're adding 2 electrons, or actually, sorry, we're removing 2 electrons. Now we have a 2+ charge. So Mg2+ typically has 12 electrons. This 2+ is actually removing 2 electrons, so -2. That gives us 10 overall electrons. So now that we have 10 electrons, I'm also going to look at and see, does everything else give me just 10 electrons? So sodium, Na. We'll see Na typically has 11 electrons. This is a +1 charge, so I'm going to actually remove 1 electron, and yep, 10 electrons. Same concept for the next one. So fluorine minus, we'll see that that typically has, and let's just look at the atomic number, that gives us 9. So there's 9 electrons, and I'm actually going to add 1 now. So since it's been -1 charge, we're actually adding an electron. So I'm going to add 1 electron, and that gives us a 10 count for electrons. All right. So lastly, let's go to neon. And neon is neutral. It's a noble gas. It already has 10 electrons. So that's why it's known as isoelectronic. Excuse me. It's known as isoelectronic because they all have the same amount of electrons. And then from there, we're really just looking at our overall trend. We could also look at, actually, we're not looking at our overall trend right now. We're then looking at our overall charges. So in this case, since they would all be the same exact atom, they would all add up to just being neon, right? If we were to do that because they all have 10 electrons, then what we look at next is really just looking at your different types of ions. So as I mentioned, anything that has a higher cation or a larger cation would then be smaller, as we saw before. And then anything with an anion or a larger anion in general, that would then be the largest in ionic radii, and so on. That's the overall concept. So just for the sake of time, I'm going to keep going. And the last trend that I will talk about is called metallic character. What metallic character is even talking about? It's really just saying, does the element behave like a metal? That's essentially it. And it's looking at the different properties of something that behaves as a metal. And your metal is going to be a great conductor. It's going to be more malleable. It's going to be easier to ionize. So ionization, by the way, is really just talking about how we're able to dissociate or break something apart. That's the idea of ionization, or just ionizing anything in general, is like how quickly or how better can we break something apart. And also, like a conductor is really saying, can it conduct electricity? That's what we're focused on. So if it has that sort of property, then it is higher in metallic character. And then our specific types then are going to be increasing as we go kind of like diagonally in our case. So as we go diagonally, and the reason for that is because right here in this corner, we should know that these are typically our nonmetals. And it makes sense that they won't behave like a metal, right? Because they're not metals. So we know that it's going to be higher in metallic character wherever we get closer and closer more to our transitional metals, which we know those can behave as metals since they are metals. So which makes more sense. So that's essentially the concept here. And if we're looking at that overall trend, let's just try one real quick. So if we're looking at that overall trend and just looking at SN, which is right here, tin, and then Te, trillium, and looking at those two and looking at our trend, since we know that it just crosses this way as we increase, then we know the one that's furthest or closest even to our transitional metals would then be tin. So tin would win in this case. It would be the most metallic character in our case. And I'm going to keep going because I really want to get to oxidation and reduction, because I know this topic is a little bit trickier. All right, why don't we first just start talking about oxidation numbers and what in the world they are and how they help us identify, what's oxidation, what's reduction, and so on. So in our case, I just want to make a note that oxidation numbers or oxidation states are not going to be your ion charges. So I don't want to say that they're the ion charges per se. Essentially what they do, it's a temporary charge, or it's a charge that tells us what that element is within that compound, but it's only used to figure out if the electrons are being, oxidized or reduced, or if the electrons are being gained or lost. So this is the overall concept of oxidation numbers. It tells us that charge of that element within the compound. All right. So let's say real quick, with water, if I knew that oxygen's typical oxidation number is a -2, then and I know hydrogen is typically a +1, those would be my oxidation numbers. And that's really just telling us what's the specific charge within this compound, what's the specific charge of oxygen within this compound. But it's really just looking at the electron flow, or are we gaining or losing electrons as a whole. So just knowing that it's really, really not your ion charges. I just want to make that note so no one gets confused with that. And let's just go into the oxidation numbers that you need to know. So in this little table, you'll see that the first type would be anything that's in its solid state. So when we have an individual element, like let's say in our case, we have Na, and it's in its solid state. Right off the bat, anything that's one individual element in its solid state has an oxidation number of 0. So I don't want you to think that, let's say if we had something like this and, it's in its solid state, boom, it's 0. No, because it's a compound. It's not one individual element. It's a compound, right? There's 2 elements within that. So that's why that would not be one of the cases. In this case, for iron chloride, that we would have to see the individual charge or oxidation number of iron and chlorine. But if this were just Fe in its solid state, it was just iron in its solid state, then yes, that would fall into that rule that, okay, it's one element, it's in its solid state, so it is an oxidation number of 0. And let's look at another type. So another type that we should know is oxygen. So oxygen's oxidation number is -2. Hydrogen is a +1. And any sort of halogen is a -1. So remember your halogens. Your halogens are bromine, fluorine, chloride, chlorine, and then iodine. So your most typical halogens that you will be seeing in these types of questions, those are always going to be a -1 for your oxidation number. And then next, your diatomic atoms. So remember, diatomic, or the di meaning two, just means that that atom doesn't exist by itself. It always wants a buddy. So in our case, I like to remember diatomic atoms. It's kind of silly, but it helps me. Chon. I like to think of it as chon as well as your halogens. So diatomic atoms, how I remember it, it's chon, meaning it's carbon, it's hydrogen, it's oxygen, nitrogen, and all of your different types of halogens. So they always exist in pairs. So carbon won't just be a C, it would be C2 or H2 for hydrogen and whatnot. So I wrote that all here. All of those are going to be an oxidation number of 0. Yep. So an oxidation of 0, know that, all right? Any sort of diatomic atom. And as I mentioned, if it helps you to remember how I learned it, was chon, and it's also your halogens. So moving on, the next type, anything that already has a charge, then that is going to be the charge, right? It makes sense. So in our case, like if we had Fe3+, then we know that that charge would then be a 3+, because it already told us that. But that's only element again. So it wouldn't be the case if we had something like this, because that's a compound that has 2 elements within. So because of that reason, no, we wouldn't just say, oh, this overall is just a -1. That's not what we're looking at. We would actually have to figure out and determine the oxidation number of each individual element before getting to that. All right. So in that case, and there's one more thing, by the way. So for groups 1, that would have a charge of +1. So remember, group 1 is really just that first column where we have, and here I can show you with our periodic table, this is group 1. So group 1 is like lithium and sodium, potassium, so on. That has an oxidation number of +1. For group 2, that has an oxidation number of a +2, +2. So those are ones that we use pretty much as like a last resort. So the ones that I put in the very, very beginning, you use those first. So you look at that and you see, okay, which elements do we have so far? And I'm going to apply those first rules. And then if I don't have anything else that I can't figure out any oxidation numbers, then I'll use the rules on the further down. So lastly, kind of use this group as a last resort. So group 2 would be a +2 oxidation number. Let's try a bunch of these, all right? So let's just apply these rules and understand how to find oxidation numbers. So right off the bat, we have Br2. Anything that's a diatomic atom, we then know it's 0. So boom, done, oxidation number of 0. Next, we have K+. So anything that already has a charge and it's already just one element would then just have an oxidation number of whatever that charge initially is. So in our case, it's just going to be a +1 because of this charge. Now we're going to start applying all these different rules and looking at this. So, okay, now we're looking at lithium fluoride and we'll see, all right, so we have a halogen, we have fluorine, right? So we know that lithium fluoride, let's see, fluorine has a -1 charge because that's a halogen. And then now lithium has a +1 charge. And we'll see that this compound is neutral. What I mean by neutral is if we were to add these oxidation numbers together, it would give us 0. And this compound as a whole didn't have a charge. Like if this had a 2+ charge or a -1 charge, then your oxidation numbers have to add up to that specific charge of your entire compound. So in our case, this does check out because both of those oxidation numbers added together do give us that neutral or 0 number or charge as a whole. So that checks out. And then now I'm going to do another type, so CO2. And we'll see that oxygen, that's one that we know, is a 2- charge. So oxygen is our 2- charge. Now I'm going to do a little bit of math here. So it's a 2- charge, but we have 2 oxygen, right? We have that subscript of 2. So in our case, I'm going to multiply that 2- by that 2 subscript, which actually gives us a 4-. Now what I'm doing right here is it's my way of pretty much figuring out how in the world am I going to figure out what carbon is? Okay, I'm looking for the oxidation number of carbon. So I don't want to say that the 4- charge is going to be your oxidation number, because it's not. It's our oxidation number of oxygen is a 2-. I'm only using that 4- to then figure out algebraically what our carbon charge would then be. So in our case, to be able to add up to 0, this must have been a 4+ charge. And if we're not sure of that, then here, let me show you a different way. Let me show you an algebraic way. So let's say if I were to do that -4 charge again, I'm going to do it a little bit differently though. So I'm going to say -4. And I know that this has to add up to 0 because it's neutral. It's a neutral compound because there's no charge on CO2. And then next, I don't know what carbon is, but I'm going to say that that's X. Yep, welcome to algebra again, right? That's chemistry for you. So now, continuing with this, I'm going to then solve for X by adding 4 to both sides to cancel it out. And there I see that X is equal to a +4. So yep, carbon's oxidation number is then a +4. So our oxidation numbers in this case would have been carbon with a 4+ charge, or oxidation number, I'm sorry, not charge, and oxygen with a 2- oxidation number. All right, is that making some sense? Please let me know in the comments if you guys have any questions, or also what you want me to talk about for next Sunday. I'm going to keep going with a couple more examples. I'll do one more, and then we're going to practice really just understanding the concepts of oxidation and so on. So let's look at something that actually is charged. So SO4 with a 2- charge. So we know in total, all of our oxidation numbers would then add up to this 2- charge. So I'm really going to put that. So 2- charge. All right. So I could even just say it, if we want to do the algebraic way, I can say it as a -2. So now we know oxygen has a -2 oxidation number. So then I'm going to look at this and say, okay, then there's 4 of them. So I have to multiply 4 times a -2 gives us a -8. And now I'm trying to figure out what in the world sulfur would be. So I'm going to label that as just X. I don't know what that is. So we have X - 8 gives us a -2. Let's solve this algebraically by adding 8 over to the opposite side. These cancel. X is now equal to 6 because we have 8 - 2, essentially. So then sulfur had to have been a +6 for our oxidation number. And right then and there, I see, okay, my oxidation numbers then are +6 for sulfur and -2 for oxygen. You'll see that oxygen's charge, or not charge, oxidation number does not change whatsoever, because that's just one that is ingrained and we just know it for sure. So other elements will change. That's why I kind of showed you all those different oxidation numbers to start off with, and those help you identify what other oxidation numbers we have for like metals or non-metals that we don't necessarily know the oxidation number. So let's put this all into practice. Let's understand the concept now of oxidation and reduction. So you might have heard this as oil rig or Leo the lion goes grr. There's a lot of different ways to know this and remember this, and whatever, if that kind of helps you remember it, then great. I have my own way of remembering this, and it's just kind of, it just makes more sense to me personally, and to my students as well. But first off, I just want you to know the concept that atoms that lose electrons are being oxidized. So if we're losing electrons, it's being oxidized, and atoms that gain electrons are being reduced. So I know it's kind of like reverse thinking in our case, where a lot of times, like, you might have seen this as oil rig, as I mentioned, and that's why it's saying oxidation is losing electrons and reduction is gaining electrons. So if that helps you remember it, by all means use that. How I like to look at this is, and we'll see this kind of more in our actual reactions, redox reactions, where if it's more positive, it's going to be oxidation. But I want you to then see, okay, well, why is it more positive? Well, electrons are negative, so I must be losing electrons, right? So as we think about it this way, kind of more like logically. So if electrons are negative, or electrons are negative people, then if we lose those from our lives, then we become more positive. So we become more oxidized. Follow me on that. And then kind of think of it as something else. Then, if we're then gaining electrons, and I said reduction is becoming more negative, then as we gain electrons or as we gain more negative people in our lives, we become more negative or reduction. Okay, that's how I typically like to look at it. It's kind of more just easier for myself and sometimes for my students to see, and I'll still keep going with that concept overall. But that's what I want you to think of. Losing electrons as being more oxidized, and then gaining electrons, it's being reduced. So we'll see with an example here. By the way, a redox reaction overall has to be a mixture of oxidation and reduction for it even to exist as a redox reaction. So just definitely know that if there's only one thing that's being oxidized and there's no reduction whatsoever, that is not a redox reaction. So it has to combine both. Now, we'll see here that I really placed all of the oxidation numbers as a whole. So carbon would have been 0 because it's individual, it's by itself. And then sulfur would have also been 0 because, once again, that same concept, it's individual element, so it's by itself, so then it has a 0 oxidation number. Now, if I were to then look at my oxidation numbers for carbon on the product side, we'll see that it became more positive. So it went from a 0 to a 4+ charge. So because that became more positive, then more positive means it's going to be oxidation. So, and then think about that again. Why is it becoming more positive? Because we lost those negative people in our lives, right? So we lost those electrons. That's why we're more positive. And then now looking at reduction, we'll see it goes from 0 to -2. So it became more negative. So if we became more negative, then we gained more negative people or more electrons in our lives, right? So that's really the concept with this. And that's kind of why I'm saying, oxidation, it becomes more positive going from 0 to 4+, and then reduction going from 0 to a 2-, and it becomes more negative. It's just kind of easier for myself and even some people to just grasp that concept of, okay, yeah, I can see it becomes more positive. Okay, yeah, I can see it becomes more negative, and so on. So in our case, since carbon changes from 0 to 4+, carbon, as I mentioned, is then losing those negative people or losing electrons, and that's why it's being oxidized. And then sulfur is going from a 0 to a -2 charge, or -2 oxidation state, I'm sorry. And then now sulfur is gaining those negative people or gaining electrons. That's why it's being reduced, or it's becoming more negative. Now that we're kind of understanding that process overall, let's continue. And now we'll throw in something else. So something known as oxidizing agents and reducing agents. Okay, so with this concept, it's kind of flipped around a little bit. I know. Why does chemistry do this? I totally get it, guys, really. I'm not a fan of it either. But oxidizing agents, bear with me with this. Oxidizing agents are going to be the element that are being reduced. So it's pretty much reversed. It's like the opposite of what you would anticipate, right? So you would think, okay, the oxidizing agent must then be oxidized. Nope. The oxidizing agent is going to be the element that's actually being reduced. And then vice versa. The reducing agent is then going to be the element that's being oxidized. So that's something to definitely know. Whenever we're looking for those agents, it's really just saying, okay, it's going to be the opposite of what I'm anticipating or what I'm thinking. And I know that oxidizing agent is actually going to be the element that's being reduced. And then the reducing agent is then going to be the element being oxidized. All right, so just knowing that back and forth. And now it's kind of like understanding, all right, what in the world is being reduced based on what we just learned? And then also what is being oxidized based on what we learned again. So we're going to see this process again. I'm just going to keep having us practice some of these because they can get tricky. So why don't we just start off with our oxidation numbers once again? And looking at this first example, we see that we have one individual element, that's sodium, in its solid state. So we know, okay, boom, that's 0. And then we also see, all right, we have a diatomic atom. So once again, that is 0. And next we'll see that, okay, we have a halogen. So we know that chlorine is typically a -1 charge, and sodium, well, that's in group 1. So, okay, that's typically a +1 charge, even though I know this kind of told us here, but still +1. And then if we were to add up those oxidation numbers, that would give us 0, which is correct because this is a neutral compound as a whole. So in our case, we'll see, okay, well, what is being oxidized? What is being, and this is a negative, what is being reduced? So, okay, I know that going from sodium it's going from 0 to +1 from our reactants to our products. Well, that's becoming more positive, right? So because this is becoming more positive, it is then being oxidized, or that's oxidation. Okay, so since sodium is then being oxidized, then I know, well, then what is being reduced? What's becoming more negative? So in our case, we'll see, okay, well, the chlorine is becoming more negative, right? It's going from 0 to a -1. So then that must be reduction. So that Cl2 must be what is being reduced as a whole. So, okay, now let's look at our different types of agents and let's see, is this going to be, a oxidizing agent or a reducing agent? And we'll come to see that since we know that this was oxidized or oxidation, I said that the sodium going from a 0 to a +1 charge or +1 oxidation state is going to then be oxidized. So if that's being oxidized, then I know that's the opposite of what I'm anticipating or what I'm thinking. So then Na must be our reducing agent. So as I mentioned here, so Na is going to be oxidized. Thus, it is the reducing agent. They're always opposite, right? They're always opposite from each other. So then now chlorine, or Cl2, went from 0 to a -1, and we said that that was reduction, right? Because it became more negative. And we'll see, all right, chlorine, so then this is going to be reduced. And then in our case, our Cl2 is then the oxidizing agent. So that's essentially the concept, and really just kind of seeing that they're opposites from each other. All right, let's keep on practicing these different types. Like I said, if you guys have any questions, by all means, leave in a chat, leave in a comment below. Let me know what your questions are. Is this making sense? And so on. So let's try another one. And let's start off with our oxidation numbers once again. We'll see that we have tin has a 4+ charge. Since it has a 4+ charge, boom, that's my oxidation number. So 4+. Okay. And then now I see, well, there's calcium, but there's nothing else. It's one individual element, so that has to be 0. And then I'll see, all right, tin has another charge again, and that has a 2+. And then we'll see, or +2. They're not the ion charges. So, and then now looking at this, calcium has a 2+. So that also has to then be our oxidation number, because remember that anything that's charged, that is going to be the oxidation number of that element. And then we'll see what happened. So let's see what's being oxidized, what's being reduced. We went from a 0 to a 2+ or +2. That is becoming more positive. So because this is becoming more positive, we are then losing negative people or losing electrons. So then that is oxidation. And then our reduction must be the one that's being reduced, right? Going from 4 to 2 or becoming more negative. So we're going from a 4 to a 2. So we're really just kind of moving, or we're being reduced by 2 electrons as a whole. We'll see that there. So because this is becoming more negative, or it's really being reduced more. So, okay, now let's go back to our concept of which one's being oxidized, which one's being, reduced, what's our agents, and so on. So as we mentioned, we said that our tin is actually what's occurred is actually going to be our reduction. And then our calcium is going to be what's oxidation is forming, right? What oxidation is happening because it's becoming more positive. So calcium is what is being oxidized. So if that's being oxidized, then we know, okay, calcium must then be the reducing agent because it's the opposite of what you're thinking. So that's our reducing agent. And then now looking at tin, we know that tin is being reduced because it's involved in reduction. So if it's being reduced, then that must be the oxidizing agent. And that's why we have that here. So it's always reversing what you're thinking. So calcium is oxidized, then calcium is our reducing agent. If tin is reduced, then tin is our oxidizing agent, and so on. And then, by the way, you'll probably notice that I'm only using the reactants part of that reduction or that oxidation. So in our case for tin, I didn't use the 2 plus, I used the 4 plus because you're looking at what you're starting with. And remember, everything that's on the left-hand side, anything that's really here, these are your reactants. So that's what you're starting with initially. So that's what's actually going to be either reduced or oxidized because that's what's going to make a change to our products. So that's essentially what we're looking at for anything that's being oxidized, anything that's being reduced, anything for your reducing agent and oxidizing agent. We're not focused on the products. We're only focused on our reactants. All right, we have time for a few more. So let's try another one. And I actually want to try something a little bit more difficult with you guys. If we have time, I'll go back to the other one. Something like this. All right, so let's just identify all the different types of oxidation numbers right off the bat. So with our first type, we'll see, all right, we have iron, and it's by itself, it's in its individual state. So I'm going to say that that's 0. Now, looking at this next type, there is a charge as a whole. Our whole entire compound would equal a -1 charge. So I'm going to start with what I know. So I know that oxygen has a -2 oxidation number. And then we'll see, okay, well, algebraically, I then have to multiply this 4 subscript with that -2. And the reason why I'm doing this, by the way, like if that concept isn't making sense, I want you to think of there being 4 oxygen. Like if I were to draw 1, 2, 3, 4 oxygen, and they all had an oxidation number of -2, because we know oxygen has a -2 oxidation number. And if we were to add up every single one of these oxidation numbers as a whole, that would be the same exact thing as 4 times that -2. And that's why I'm using that. That's why I'm just multiplying them right off the bat. So I hope that this makes more sense now as to why in the world am I even doing that. So it's just because there are actually 4 oxygen. That subscript tells us that. And then that's why I'm just multiplying 4 times that -2, which then gives us -8. And this would also give us -8 if we were to add them all up that same way. So continuing with that concept now, I'm going to now set this equal to the charge of the overall compound, which is a -1 because of this charge right here. And now I'm trying to figure out what in the world am I doing? So what is this oxidation number here? I'm going to put that this is an X, and we'll see with that. So if this is X minus 8 and it equals a -1, then I'm going to try to figure out what our X would actually equal. So I'm going to add over that 8. And X would equal a +7. So, all right, we have +7 for manganese. So manganese, or Mn, would then be a +7 oxidation number. And then from there, I'm just looking at, so I did all of this algebra and all this work just to figure out what in the world the oxidation number for manganese was. So I'm going to erase this now because it is not part of your oxidation number. Your oxidation numbers are these: the -2 with your oxygen. That's only going to be your oxidation number. It's not going to be the -8. And then your +7 for your manganese. And I'm going to keep going. And then keep going with this concept. We'll see that our hydrogen already has a +1 charge, which we know that is going to be the oxidation number either way. And then iron has a 3+ charge here. So then that has to be the oxidation number as well. And next, I'm going to keep going and just looking at these different charges. And we'll see that oxygen here, once again, oxygen has a -2 oxidation number. And we're going to multiply. We're going to multiply by 2, so that would give us a -4. And there is no charge in this case, so it would equal a neutral compound, or it would be 0. And then we're trying once again to figure out what in the world manganese is. So I'm going to add over that 4 to solve for X. And that would give us a +4 oxidation number. And erasing this because this is not your oxidation numbers. It's only that +4 and that -2. And then lastly, looking at water, we know that your oxygen, once again, is -2. And then our hydrogen, if we were trying to figure this out, even though you do know that hydrogen is +1, I'll still show you how I know, looking at all this. So we can do this whole concept again, where this would have been equal to 0, actually, because it's a neutral compound. And then now what I could do with this, if I didn't know what hydrogen's oxidation number was, I could have said, well, there's 2 of them. So if I were to do this algebraically, this would have been 2x. Does that make sense? Because there are 2 atoms, I am now saying there's a 2 in front, and I'm going to then solve for what x is. So I would then add over that 2. Those cancel. This is 2 is equal to 2x. And I divide this 2 because they're being multiplied, and I want to get rid of that. These cancel. X is then equal to 2 divided by 2, which is 1. So then this gives us a +1 oxidation number and a -2, as we saw before, for actually +1. I'm sorry, +1. And we know that that actually is true. The oxidation number for hydrogen is +1, and the oxidation number for oxygen is a -2. So did all that algebra just to figure out, in case you didn't know, but if you do remember that chart that I mentioned in the very beginning, it is really helpful to just know that hydrogen is a +1, and that's not going to change. So looking at all this, these are all your different types of oxidation numbers. Hope this really helps you guys understand how to figure out oxidation numbers as a whole. I know I'm out of time, but I'm going to just look at this real quick with you guys, just seeing what we would have gotten. So in our case, all of our oxidation numbers are as shown, and we'll see that we have iron as 0, and then we're going from 0 to a +3. So that's becoming more positive. That's why that's being oxidized. So we have oxidation in this case. So what is being oxidized is our iron. This iron right here is being oxidized. And then we'll see that, okay, our reduction process, note that it's not going to be your oxygen. We're not focused on oxygen because oxygen's oxidation number will always be a -2. That's not going to change. What's changing here is Mn, or manganese, and we'll see that that's going from a +7 to a +4. So it's being reduced because it's going down. It's becoming more negative. And then in our case, we'll see that this entirely is then going to be what's being reduced, because we always look at what is in the reactants rather than what's in the products, because that's what's going to actually be oxidized or be reduced, is what we initially start with, which is always in your reactants. So now looking at this, if iron is being oxidized, then that must be our reducing agent, right? Back and forth is always the opposite of what you're thinking. So that's why iron is your reducing agent. And then now we'll see that manganese, or that initial reactant that we'll see, is going to be the oxidizing agent because it is being reduced. So always just opposite of what you're anticipating or what you're thinking as a whole, and so on. All right. So overall, we went over to pretty much just talked about everything with oxidation and all your periodic trends. Definitely write those down, make flashcards if you need to. What helped me overall was just practicing a ridiculous amount of practice problems and just looking at this over and over again. Personally, that's the main, process and key for education. That's how personally I succeeded with my education and was able to just understand these concepts and now even teach them, was just repetition. So I would write my notes over and over again, just trying to just then figure out, okay, is there an easy way to look at this? Now that I finally understand the concept, if I were to do these practice problems over and over again, will I get them wrong? And I'd kind of test myself with that. Another thing that I also wanted to mention with you guys is if anyone struggles with test anxiety, I personally struggled through it for a good amount of time, where I would freak out on my exams, and I never really felt like I would go to the exam and then my brain would just go, nope, we don't remember a thing. And that kind of test anxiety, how I overcame that and how I moved through that was really just, I would put myself in that environment beforehand. And I would literally time myself where I had like my practice problems, and I'd put a timer, and I would kind of really get prepared for that anxiety, or get prepared for that kind of like feeling of being in that atmosphere of my exam. So that really personally helped me. And now I can, happily say that exams don't really scare me anymore, or, after I did that, I really then succeeded. But that's just something I wanted to mention for you guys. And another thing, as I keep mentioning, please, oh, please, let me know what you guys are working on, what you guys need help with. I want these Sunday sessions to really just be helpful for you guys. Feel free to ask me questions. Jessica's already letting me know what she needs help with. Thank you so much. I just really want to know what you guys need help with. And also reserve your spot for next week. I will be letting you guys know what I will be covering for next week. As I said, I just really want to get ideas. Let me know what you guys are working on, what you need help with. And please share and like my videos and just spread the word so I can do an 8-hour live session for you guys before your finals. And thank you so much for being here. I'll see you guys next Sunday. See ya.